Last time we ended by having the desire to be able to write a circ operation on DFAs, where we could take one DFA A and another DFA B and then circ them together. So let's think more concretely about what exactly this means. Let's first start with a little example. So recall that previously I mentioned how circ makes sense on individual strings. So we could write jm circ x, and that would be the same as the string jmx. So that defines the circ operation on individual string elements. But we can also define circ on entire sets in the following way. So imagine we had the set containing j, and we had the other set containing x and y. So what would the circ of these two things be? Well, it's kind of like the Cartesian product in that we're going to circ each one of them. So this is going to be equal to jm circ x and jm circ y. So in other words, W is a member of A circ B if and only if W is equal to x circ y, where x, so there exists an x and a y, so that's that W is equal to x circ y, where x is a member of A and y is a member of B. So that is a way of defining what it means to circ, what it means to circ concatenate, that is, concatenation, what it means to concatenate sets, and a more general definition of that. Now, we can take individual examples of this and circ them manually. For example, suppose that we wanted to take these two DFAs and circ them together. Well, what's the machine for the language JM? Well, we have a machine, a state where when we see a J, we go here, and when we see an M, we go here and we accept. And for XY, we have a state where if we see an X, then we go here, which is accepting, and if we see a Y, we go there, which is accepting. So how can we combine these together? Well, what we can do basically is we can take this start state right here and paste it on top of that end state. So what we can do is we can construct the combined one, jmx, jmy, by if we see a j, we go here. If we see an m, we go here. If we see an x, we go there. And if we see a y, we go here. So you notice that what we did is we took this part of the machine from here and this part of the machine from here. So it's basically what we did is we took this machine and we pasted it on top of that one in the final position. So that's an intuitive way of thinking about what concatenation means when you think about it in terms of machines. You run one machine, and then when that machine is over, you run the next machine. Hold on 1 second. That was my first time pausing. We'll see if it worked. All right. Okay, so the basic idea of concatenation is you run one thing and then you run the next thing, which we can represent by taking the second machine and pasting it on top of the other one. Now, this is a little bit strange if we were to think about it in the opposite order. So for instance, suppose that what we did is we instead did x comma y circ jm. Well, here we would essentially be pasting the machine 2 times. So we would have the start state. On an x, we'd go here. On a y, we'd go here. And then, well, what we want to do is we could paste on the other machine, so j, m, and then do it again, j, m. But clearly, if we were designing this by hand, we wouldn't do that. What we would do is we'd just combine them into one. So we would say, if there's an x, we'd go here. If there's a y, we'd go there. and then they would merge on a J, and then on an M they'd go here. So this is what we would probably do by hand, and this is what the pasting logic would have us do. This whole pasting logic is a little bit more complicated too when we think about examples where we're thinking about the circuing of two languages that are themselves infinite. So suppose, for instance, that we wanted to take the even length machine. So here's a machine for strings that are evenly long. And here's one for ones that represent an even number. And how do you know something's an even number? It ends in a 0. So the empty string represents an even number. If it has only zeros, it ends in 1. If there's a 1, and then if there's a sequence of 1s, and then another 0, and this one. Okay? So now imagine that we wanted to write down a machine for even length, circ, even number. So that means that we have an even number of characters, and then after we've seen an even number of characters, then we see an even length. Well, it's a little bit weird to think about how to do this, because how do we paste this start state onto that end state? Does that even make sense? I mean, if we literally did it, then we'd get this weird, first of all, let's write down 0, 1, and 0, 1 here. If we literally pasted it on top of, we would get something that would look like this. We'd have that start state, then it would go over here. Let's just label these A, B, X, Y. So this is A, and it's going to be X because we pasted onto it. And so on a 0 and 1, it's going to go over to B, which on a 0 and 1 would come back here, but also it's going to go back to itself on a 0, and on a 1, it's going to go over to Y, which goes to itself on a 1, or back there on a 0. Now this doesn't make any sense because it says it's got to do this on a 0 and that on a 0, which violates our rules. Because remember, these are pictures of graphs, and the graphs have only one labeled edge for each character in the language. So it doesn't make sense for how to do that. So this idea of this pasting is not a general tool, but it is possible for us to come up with an even length and even number machine. And here's how we could do that. So we got to think a little bit harder though. So what does it mean for something to be an even length followed by an even number? Well, think about this. So is it the case that, okay, so think about it like this. Imagine that you had something that was evenly long, but then ended in 1. That would be rejected because that second one wasn't an even number. But if it was oddly long and then ended in a 0, it should be, quote, rejected because, but actually that oddly long one, we could just take whatever the last character was and say that's part of the even number, and then it doesn't matter what it is. So that really means that all this is really saying is, does it end in 0? Because if it ends in 0 period, then it must have also had an even number. Essentially it doesn't, putting even length in front of this doesn't actually accept any more strings, because an even number is allowed to have even or odd length things in front of it. So if we think harder about this, we know that even length concatenated onto even number is actually just the same as even number. So we don't even need to draw something. But that's something that we would only know by thinking really hard about it, not something that we could derive automatically. So let's put a pin in this for a moment and think about other operations that we might like to do on DFAs. We might like to do a reversal operation. So we'll say, so for instance, we could have JAY, and then reverse would be equal to YAJ. That's something where it's kind of intuitive to think about how this would work. We would have a start state that on a J we'd go here, on an A we'd go here, on a Y we'd go to an accepting state. And if we wanted to reverse this, we could just reverse the direction of the arrows, make this the start state, and have them go in the other direction. So specifically what I mean is that if we saw a Y, we'd go here. If we saw an A, we'd go here. And if we saw a J, we'd go there. Now, again, this is something that intuitively makes sense to us. We can just reverse the direction of things, but it's a little bit more complicated if we were to have a machine that had multiple options. So for instance, imagine that we had the following. So imagine that we had the language JX and JY. So we would start, and we'd see a J and go to here, and if we saw an X, we'd go here, and if we saw a Y, we'd go there. Now, how do you reverse that? I mean, obviously, it would end up as XJ and YJ, okay? But we couldn't have a start state that was two different places. One when you saw an X, one when you saw a Y, they both got here, and then when you saw a J, you got to there. That doesn't make sense because you can't have two different start states. That's not allowed. We would have to think harder and come up with a way for doing this by hand. And that way by doing things by hand, of course, would be we'd have a start state, and if we saw an X or a Y, we'd go here, and if we saw a J, we'd go there. That's the way to come up with it ourselves. So what I'm trying to get at with these two examples is that circing is something that intuitively makes sense. We should be able to do it on strings, and thus on languages, and thus on DFAs. But a simple way of doing it where we paste start states on top of end states doesn't work because we get into these crazy situations where we're supposed to do two different things on a zero. Similarly, if we think about reversal, where intuitively what we do is we just reverse the direction of the arrows and make the start state the accepting state and the accepting states the start states. But that doesn't make sense because we get into this weird situation where there are multiple start states, and that who knows what we're supposed to do for that. One thing that we could do with this whole multiple start state thing is we could say that there is one start state, but that somehow it's supposed to do something on nothing, where if it got nothing, it would go to a state which is like the previous accepting states. And then those, when they saw J, they would go there. Where if you could somehow have a transition, this, by the way, right here is an epsilon. If we zoom in, what I'm writing there is epsilon. If we zoomed in and we saw epsilon, then this would be like a new thing that we could have that would allow this to work. What we're really getting at is that there are these operations that we want to do on DFAs, the concatenation and the reversal operation, that we can't do because it's too complicated to think about what the DFA is. Now, this is an example where our representation and our definition of these kinds of machines is really failing us. That there's something that we would like to have that we can't. So, if we were a physicist or something like this, we would just throw up our hands and say, well, that's just not the way the universe works. We can't do anything about it. But the nice thing about computer science is that we get to make the rules. So how about we just make a new kind of machine that does allow exactly these kinds of things? Let's allow a machine that allows us to do two different things on the same input and allows us to do transitions without actually changing any characters. So that's going to be a new kind of machine called an NFA, a non-deterministic finite automata, and we'll look at those in the next video. Today was a really short class. It's fine.